From today, we will start with the detailed discussion on this. So first, today we will start with the shunt compensation. Okay, so we'll go one by one. So there are two types of compensation as we have discussed yesterday. So we'll go one by one first. Okay, so the first we will start with shunt compensation. So we are having two. So any we'll discuss what is shunt compensation. Any idea, Roshan? Shunt compensation. Roshan, can you speak? What is shunt compensation?
In parallel, sir.
Huh?
Compensator used in parallel.
Compensator. So what it does? What it does? Current injection, voltage injection, what it does to the line?
Current injection, sir.
Which one? What?
Current, sir.
It will inject current to the system.
Yes, sir.
Shunt, na? So shunt nadi, it injects current to the system or voltage to the system.
Current.
So actually shunt nadi, it injects current to the system. Okay, so current it will inject. So like if you have seen the basic types of FX controller, now we have seen that. So shunt compensation. We'll see. Shunt compensation, actually they are connected in parallel. Okay, so parallel with the power system. So this is the case we have already seen. Okay, so the power system, this one. So shunt compensation are connected in parallel. So parallel with the power system transmission line, and it works like a current source. Okay, so that means it injects a current, controllable current. So it injects a current to the transmission line. And then the main objective of this shunt FACS devices is to supply this reactive power demand to the line. So reactive power. Okay, so the main objective of this shunt compensation, and that is what you have. Then, like if you see, the reactive current is injected into the line. Okay, so it is injected line. How it is injecting is by wearing this shunt impedance. Okay, so that is where you listen. Therefore, this transmittable active power is increased. So active power is increased, but at the expense of this increasing reactive power demand. So as the transmittable active power is increased, the demand for that reactive power will also increase. That is the Nichi, or at what cost it is in. You can inject the current, reactive current, to the system by wearing the shunt impedance, whereby increasing the active power, but it results in the increase of the reactive power demand. That is another thing you have to keep in mind. So there are two methods wherein you will do this shunt compensation. There are two methods by where you can have. So first one is shunt capacitive compensation, and then second one is shunt inductive compensation. So you have two methods. Okay, so these two, shunt capacitive and shunt inductive. So in shunt capacitive compensation, what it does is it is used to improve the power factor of a system. Okay, so power factor of a power factor of a transmission line. So how that capacity or capacitor improves the power factor? Any idea? Anyone? Any? Hello, Namit. How capacitor improves the power factor of a system?
No idea, sir.
No idea. Kinle Wangshu, any idea? Kinle, any idea? Kinle, are you online?
Yes, sir.
So any idea how it is used to improve the power factor, capacitor? Samjana, any idea how it is capacitor is used to increase the power factor?
Don't know, sir.
Oh, okay. So if you all are not able to answer, please check it. You have already studied, because it actually draws a current from the line which actually leads the voltage by certain angle. So already the lagging current, which is drawn lagging current, so it will try to compensate it and then try to minimize the angle of lag. So thereby it will improve it. Okay, so like suppose if suppose the current here, so okay, so this is what you are having. So whenever our inductive load is connected to the transmission line, power factor lags because of the lagging load current. And to compensate it, a shunt capacitor is connected, which draws current leading to the source voltage, resulting in improvement. So this is how it is actually doing. So like if you can see, I'll try to draw it. Say suppose this is the voltage V. Now say suppose the current is lagging here. This is your I drawn by the system, which is lagging behind voltage by angle phi. This is without any shunt and capacitor. Now if you connect a capacitor, then what will happen is this is your current IL, say suppose inductive load ki current. Now if you connect a capacitor to the system, then what it will do is it will draw a current which will lead the voltage by this. So this one will be your IC. Okay, so IC you can have capacitive current which will draw this. So this is your another phi, say suppose phi 1. Okay, now the resultant current somewhere else here. So now say suppose the resultant of these two will be your somewhere else here, resultant IR. So this is what, so this is your IR resultant, which is phasor sum of IC and IL. Okay, so this is your resultant current. And now if you see this phi, say suppose this is phi 2, which is the angle between the voltage and resultant current phi 2. So now if you see phi 2 is smaller than phi 1, means phi. So which means the power factor has improved. Okay, so this cos phi has improved at last. So this is like, say suppose now you can consider cos 6. If this angle, say suppose if this is 60, what will be the case? Now the angle has reduced, say suppose 35 now. So then the cos phi will be improved. And this is how it is there. So whenever an inductive load is connected to the transmission line, so most of the load are industry loads, and that are like induction furnace, the induction motor, and so that is there. So therefore the load is usually inductive in nature. Any idea types of load?
Resistive load.
Resistive load,
Inductive
capacitive
load.
inductive, and then and the most commonly or dominant load is this inductive. Okay, so this inductive, the dominant mostly then, because of the industries and all this thing, and that is where. So because of the fact of because of this, inductive current IL will be drawn by the system, which lags behind the supply voltage by angle phi. So now in order to do the improve the power factor, we are using the shunt capacitor is connected. So when you connect this is how it is. Then second type you have is shunt inductive compensation. Okay, so now here you are using is inductor is connected in parallel with the system. So this type of compensation is used for charging of the transmission line, or when there is a very low load at the receiving end. So whenever there is, so now when the transmission line is lightly loaded, then we give it as the shunt compensation is used. Okay, so this is another type of compensation you have. So and now here you are having is due to very low load or no load, very low current flows through the transmission line. So in order to have that current, normal current to flow through this, inductor is connected in parallel with the line. Okay, so this is there. Then another one you have is shunt capacitance in the transmission line causes voltage amplification. That is Ferranti effect. Ferranti effect. Gachina, what is Ferranti effect? Anyone? Ferranti effect? Kencho? Ferranti effect?
The receiving, the voltage at the receiving end is not equal to the sending voltage.
So this is there. So this here, in order to, like here it is given, okay, the receiving end voltage may become double the sending end voltage, very long time. So to compensate this, shunt inductor is used. Okay, so inductor Ferranti effect, the receiving end voltage is greater than the sending end voltage. So this is in order to make the receiving end voltage more or less equivalent to the so that is used. Okay, so this is what you will have. Is it okay? Okay, so now shunt compensation FX devices are in. Okay, so this is the same thing. Then another one is now the objective of shunt compensation. Okay, so objectives of shunt compensation is what you have is the transmittable power can be increased and the voltage profile along the line can be controlled by appropriate reactive shunt compensation. Okay, so the main objective CD, what you can do is one is the power transfer capability can be increased, and then another one is to improve the voltage profile, means there won't be voltage sag nor voltage swell. Okay, so just to keep it there, so we are having, so and then how it is, so two an objective dynamic, that is to increase the transmittable power and to make the voltage profile and to control the voltage profile of a line. So how it is done? It is done by using this reactive shunt compensation. So reactive shunt compensation is there. And the main purpose of this reactive compensation is to change the natural electrical characteristics. Okay, so natural electrical characteristics, like so normal characteristics of the electrical parameters, to make it more, so what it will do is compatible now, and compensation the main, so now you will do it compatibility. So how you, so see, natural is transmission power, give say suppose 5 megawatt you want to transmit it. Now the demand, say suppose the demand has increased to 10 megawatt somewhere else, then you can use this shunt compensation to increase this. Okay, so prevailing load demand, so that is what you will do. So depending upon the depth, so you can either increase or decrease. Okay, so therefore what you have is shunt connected fixed or mechanically switched reactors are applied to minimize the line open voltage. So this is there. Therefore, in order to do this, what you are doing is you are connecting either shunt connected, either it can be fixed or mechanically switched reactors to minimize the line over voltage under the light load condition. So if it is during the light load condition, in order to not to have Ferranti effect, you can have this. Or shunt connected or fixed mechanically switched capacitor, you will use this capacitor if you will be using the capacity, you will be using this inductor or reactor if the transmission line is lightly loaded. Okay, so if the transmission system is lightly loaded. Now if the transmission system is heavily loaded, what you can do is you will connect the capacitor in parallel. Okay, so this, so if the power system is heavily loaded, the fixed or switch capacitor is used for maintaining the voltage level. Okay, so just main voltage profile, that is what you can. So finally, if you can see is the main or ultimate objective of applying the reactive shunt compensation is to increase the transmittable power. So that this is the increase the transmittable power. So why we required this objective is, again, another thing is to improve the steady state transmission characteristics as well as the stability of the system. So first objective is to increase the transmittable power. Also, it may be required to improve the steady state transmission characteristics as well as the stability of the system. So three objectives. So therefore, why we use this reactive compensation is, one is for the voltage regulation at the midpoint or some intermediate to segment the transmission line, and at the, so this is one. So first one is segmentation, transmission line segmentation. Second one is to prevent the voltage instability. And then another one is dynamic voltage control to increase the transient stability and damping out the power oscillations. So four war compensation you may run that these are the, so out of which I think you might have done voltage and instability you might have done stability done, you might have done the power and oscillation
Yes,
also,
sir.
and this Tigara you might have done, no, because this one you use even in machine we have done this one, two equal area criteria. Can you recollect now this one? This stability na equal area criteria. Anyone? Can you remember now that one? Equal area criterion.
Yes, sir.
So equal area criteria given, that is where you will have, or the swing equation. Swing equation, remembering now?
Remembering, sir.
Swing equation. So can you tell, Roshan? Swing equation is equal to final one. D2, D something like that you can show.
Sir, formula di misalnya ni graph jam di sila, sir.
Graph D chana ya. Whiteboard na. Okay. So swinging, from where it will start swinging? So from here you will have another, no? Equal area criteria. So
Ani belum sir baru.
anyway, then this, the rotor will swing this way, up and down. So swinging the loop, then the swing there. So now if it swings, if it go beyond this, then the machine will become unstable. Okay, so this is what actually it means. So stability done. So now here we will be just in detail, we will be using this midpoint compensation for the transmission line segmentation. Okay, so transmission line segmentation, and then to improve that one. So we will see this one. So first one is midpoint voltage regulation for line segmentation. Okay, so the consider a simple two machine system. So two machine system you can have.
J PM minus PE is equal to JM by G del. Ini kan jadi mana swing equation?
Okay, so now you consider this one. This is your two machine system. Okay, means a transmission line ki generator chi the load. Now here you are having is two alternators together connected by a transmission line. So okay, so this is your two machine system. This first A. So we are considering this one. So consider a simple two machine or bus transmission model in which an ideal wall compensator is shunted at the midpoint. Okay, so this one you can see. So this one, this, okay, so it is shunted at midpoint. So this ideal compensation is there. This is at shunted compensation. So active power is 0 here. So so the transmission line, it's broken down into, so it is broken down into two here. So half bit. So X, otherwise the transmission line is there. So otherwise how it will look is like, actually it is like this. Single line diagram they are watching. This is your generator A, then actually transmission line is there, and then your generator B. Two machine system, and that is what there. Then this is your VS, this is your VR. Okay, and then this is your X transmission line. Now this one, now you are giving compensation at midpoint. So say suppose you are giving here compensation. This is your compensation. You are giving some reactive power, injecting reactive power. So now in this case, this one will be your X by 2. This one will be your X by 2. Okay, so this is what you, and this is here you have is VM. This is your midpoint voltage. So exactly at midpoint you are having this. Okay, so this figure, have you understood this one? Hello.
Yes, sir.
Okay, so this is what we have. So this is midpoint. Now for simplicity, line is represented by series line inductance only, no resistance and all this thing, nothing. So we have neglected that resistance as of now. The compensator is represented by sinusoidal AC voltage source, as we have seen, that is there. And then this, for the analysis part, we are assuming that the midpoint voltage is equal to sending end voltage is equal to receiving end voltage is equal to the V. Okay, so then another point, as I have already told you, the figure, the midpoint compensator segments the transmission line into two independent parts. We have seen, no, the part 1 and part 2. So this is with impedance X by 2, which carries power from this one, which carries part 1 is from power from sending end to this midpoint, and second part also, which has got another half of this reactance, will carry power from midpoint to the receiving end. Okay, so this is what you have. So two. So this one, if you can see, okay, so now two parts, it is broken down into two parts. One is first half from sending end to midpoint, and second half midpoint to the receiving end. It will carry the power. So now from figure you can see. So now can you draw? Anyone like, so see this one from figure 9.1. So from this figure, can you draw? Now can you find out the relation between these three? Vs is equal to, can you find out? Vs is equal to, anyone? So here Vs is equal to what you have? Anyone? Vs is equal to, hello, anyone? Vs is equal to
VM
Vm, okay,
plus
Vm plus
IMR x
I
by 2 M
ISM. Okay, so this ISM is nothing but ISM is actually current from sending end to the midpoint. Okay, so this is your ISM, because later on this equation is required while drawing the phasor diagram. ISM by x by 2. This is there. Then similarly, can you go for VR, receiving end voltage?
VM
Anyone?
minus
Huh?
VM
VM
minus
minus VM minus
IMR
IMR. So
x by 2.
IMR x by 2. So these are the two governing equation to draw this. So now by using these two equation, can you all draw the phasor diagram? Okay, so please draw the phasor diagram by using these two equation. Everyone start drawing and then you find out. So this is what you have. So as this one, that will be Vs is equal to Vr plus Jix G yani. So another equation you have is this, and another one is this. So now can you draw the phasor diagram? Draw phasor diagram. Draw the phasor diagram, everyone. Drawn. Drawn phasor diagram. Hello. So drawn phasor diagram. Sanjita, have you drawn?
Doing that.
Okay, can you show? Okay. VM, VS, okay. And this is your V. VR. Okay. So Anzubli, similar you will have. Okay. So this is ISM, ISM, JISM x by 2. Again from here you will have is another one. Okay. So can you raise it, Sanjita? Okay, so this is what we will have. See the phasor diagram you have seen is this is your VM, VR, VS. So VM is equal to VS plus ISM JX12. Then VS is equal to VM plus this. Then VR is equal to VM minus VS and the minus zero that is there. So VR plus this one will give you VM. Okay, so VR plus this will. So this is what how it will look like. Now, if you see so now in this case midpoint war compensator exchanges only reactive power. Okay, so only reactive power during this process. Then now if you see for the lossless system, so what is lossless system? Roshan?
Sir,
Huh? Lossless system.
so
So lossless system, you are assuming this is this you are assuming as lossless system means R is equal to R is 0. Okay, so lossless that is what you have. So now from phasor diagram and all this thing, if you see this VSM and all this thing, you see, and so this power P, when you derive it, you will get this power. So this is power, you are getting power. Okay, so del by 2 power. This is what. So now if you see this, the power done. So now from here, if you see as the compensation increases, so the max now we have this, no? Power angle characteristics. If you remember in alternator, we have like this, no? Emo. This is the case, no? Power angle characteristics. This is P max. When used to be P max? At what angle will the power be maximum? So you get in at what angle the power will be maximum? At what? This one, del. At what del will the power be maximum? Anyone?
at 90 degree.
So when del is 90 degree means you have like this, no? We have P is equal to V1, V2 or Vs this by X sine del. So now when you plot this against this, you will get this one. So maximum power is at angle is equal to 9. So now if you plot this way, so this is your P, or this you can have del, this is your P. So when del is 0, what will be the value of P? Sine 0?
0.
Then when del 50 degree, what you will have? Something you will have this, no? Then 45, 60, then 90. So you will get this. So now when you plot, you will get this graph. So this graph is actually this one. This is the graph. Okay. Now when you are using the midpoint compensation, so when you are using this compensator, okay, then you will get power is this. So now the power has increased. See, the power, maximum power has been increased to this. It has increased. Okay, so the power transfer is increasing by 2-fold. Similarly, reactive power, and we have seen, no, at the increased reactive powers, you see, the reactive power has also increased at this. Now again, if you go up, then another, if you increase another compensator, then again the power will become more. So, and that is where you are. Okay, so the angle at which the maximum power is occurring is increasing here. So double the angle at which the power is doubling is 180 degree. Now 4 times we are watching again same reason, but at this cost. Okay, so the active power, transmittable active power is increasing at the increase reactive power. Okay, so this is what it is actually. So this, now when you use this shunt compensation, it will increase like this. Okay, so this is the case to Pmax. Okay, so when you plot for this, you will get, so with shunt compensation, see the active power is almost doubled, but even the reactive power has been, demand for reactive power has been increased. So this one in the beginning of the narrowing actually. So if you see, if you see the here, the purpose of reactive compensation is to change the, we have one more line here. The reactive current is injected into the line to maintain the magnitude by varying the shunt impedance. Therefore, the transmitter active power is increased. So this one is increased, but at the expense of increasing reactive power demand. So this one is actually evident from the graph. Okay, so evident from this graph. So this graph, if you see, so evident from this graph, that again, the one which we are using is evident from this graph. Okay, so this one, at the increased reactive power. So this is where it is going. Okay, so this is increased. The active power has been increased, but the demand for reactive power has also increased. Okay, so
Yes,
direction,
sir.
you take it, the direction and the beam, that is what you. So now if you see this, the midpoint shunt compensation can increase transmittable power almost doubling at the expense of rapidly increasing reactive power. So this is what, and also on N generator, so it will increase in both the case. Okay. Now the question here is why the compensation is exactly used at midpoint? Why not 1/3 of the line, or why not 2/4 of the line, or 1/3 of the line, or 2/3 of the line? Why exactly at 50%? So why? The reason, there are two reasons. One is the voltage sag. So for the uncompensated transmission line is maximum at midpoint. So in order to find out that voltage sag at that one is max. Also, it breaks, another one is from the easy, and it breaks the transmission line into 2 equal halves, so that the maximum power transmittable is same for in this. Then if you are using this for unequal segment, the transmitter power of the longer segment would certainly determine the overall transmission limit. So the longer line, that is where you. So now you can use this concept of transmission line segmentation, and then can be expanded to multiple line compensators. Okay, so at equal locations, at equal segments, you can use, so this type. So you can use VS compensator 1, compensator 2, compensator 3. So you can use this compensator to do the compensation of line. So if you are using, then what you'll have is 1, 2, 3, 4 divided by 4. Okay, so the line is divided into 4 and then do the compensation. Okay, so why we are doing the compensation, you got it? No, now for summing up, any points? Can you tell now why we do compensation? Hello. Why compensation? Hello. Why we use compensation? Okay, so please check it. So today we'll stop here. So any doubt, anything?
No, sir.
Okay, so now we'll stop here.
Thank you, sir.
Okay, thank you.
Thank you, sir.
So I'll,
Thank you, sir.
okay. I'll upload the slides as we finish. So I have uploaded. Okay, yesterday's one I have uploaded. So please check it. If you have any doubt, please send
Yes, sir.
to mail or you can send it here
Okay,
also.
sir.
Okay, sir.
Thank you. Thank you.
Thank you, sir.
Thank you, sir.